Okay, in this video we're going to take a look at finding roots of complex numbers. And this will be the last topic we cover in this section. So recall that taking the nth root of a value is the same as raising that value to the 1 over n power. And finding roots of complex numbers, we're going to kind of reverse de Moivre's theorem, which raises complex numbers to powers to get the roots of a complex number. So if w and z are complex numbers, and there's a natural number like 1, 2, 3, 4, 5, etc., such that w to the n equals z, so w to the nth power equals z, then w is an nth root of z. So we're going to use a little variation on de Moivre's theorem to find those roots. So if z is a non-zero complex number and its polar form is z equals r cis theta, then for each natural number that we're using as a root, z has n distinct nth roots. A little bit like the fundamental theorem of algebra, where if we have a fifth degree polynomial, it's going to have 5 zeros, real and or complex, or at least complex. So the distinct roots are going to be these w's with subscripts. We're going to start with 0, and if there's n of them, we actually go up to n minus 1, where each root is the nth root of our modulus times cis, the angle that we're going to get, plus 2 pi k or 360k, divided by whatever our root is. So this looks really complicated and scary looking, but you can work with degrees and then convert your answers to radians. So that's what I would recommend for these, especially if you get something like theta equals pi over 3, and then you have complex fractions, and it's just simpler to work with degrees and convert your answers to radians. So find each of the following. First up, both square roots of z equals negative 2 plus 2i times the square root of 3. So if we were to take the square root of both sides, we'd get one positive, one negative root. We're going to see how that plays out with this complex number. So writing it in polar form, we get modulus is 4, x squared plus y squared is r squared, and then the angle is 2 pi over 3, or 120 degrees. So I'm going to use 4 cis 120 degrees because the degrees are easier to work with. So we're going to take the square root of 4, and then we're going to take that 120 plus 360k, and since it's square root, we're going to divide it by 2. So square root of 4 cis 120 plus 360k all over 2, which is cosine 120 plus 360k over 2 plus I sine 120 plus 360k all over 2. And this is kind of reminiscent of when we solved trig equations. If we would have something like, let's say cosine 2 theta equals negative a half, something like that. So in this case, we're very similar to how we did trig equations, where we have our angles. In this case, they're both going to be the same angle, plus 360k, or period for sine and cosine. And since it's square roots, we're dividing them by 2. So 4 to the 1 half, or the square root of 4, is 2. And then 120 divided by 2 is 60, and 360 divided by 2 is 180. So we could write this as 2 cosine of 60 degrees plus 180k plus I sine 60 degrees plus 180k, or if you don't want to write out that much, 2 cis 60 degrees plus 180k. Well, our angles, we're going to start with 60, so 2 cis 60, and then if we add 180 to that, we're still in between 0 and 360, so 60 and 180 is 240. If we add another angle, or another 180 degrees to that, we're going to get a coterminal angle to 60. So if we kept going, we would just alternate back and forth between these same 2 points. So 2 cis 60 degrees and 2 cis 240 degrees. And then if we wrote those in rectangular form, it's 1 plus I square root of 3 and negative 2 plus 2I square root of 3. All right, part B, the 4 fourth roots of z equals negative 16, or z equals negative 16 plus 0i. Negative 16 plus 0i in polar form is 16 cis 180 degrees, or 16 cis pi radians. So we're going to take the fourth roots of that, so 16 to the 1/4 power, or the 4th root of 16, and then cis 180 plus 360k, and since they're fourth roots, we're going to divide that expression by 4. So when we simplify, 16 to the 1/4 power is 2. If you can't simplify it, or if it doesn't simplify to a nice integer number, just leave it as simplified as you can. But here we have 180 divided by 4 is 45, and 360 divided by 4 is 90. So we're going to, just like with trig equations, we'll start with 45, and then we'll just keep adding 90 degrees until we get, beyond 360. So we have 2 cis 45 degrees, and then 90 and 45 is 135, so 2 cis 135. Add another 90 to that, you get 2 cis 225, and add 90 to that, you get 2 cis 315. If you added another 90 degrees to that, you get 405, which is coterminal to 45. So, whether you go forwards or backwards, adding multiples of 90 degrees, you're just going to cycle between these two or these four values. Interestingly enough, for roots 3 and higher, so cube root, fourth root, etc., if we plot these 4 points, or here we go in their rectangular form, if we plot these 4 points either in their polar or rectangular form, notice they make a square. 4 points will make a square. 3 points will make an equilateral triangle, and in general, however many roots you have, that number will equal the number of points you can plot, and it'll be a regular polygon. So 4 fourth roots is going to make a square. The 5 fifth roots would make a regular pentagon where all side lengths are equal and angle measures are equal. So as far as the visualization of what's happening when you're taking roots of complex numbers, you're creating these regular polygons in the complex plane. So 3 cube roots. Well, again, if we plot our 3 answers, it will make an equilateral triangle. But square root of 2 plus I square root of 2, polar form is 2 cis 45 degrees. And then we're going to take the cube roots of these. So we have 2 to the 1/3 power, or the cube root of 2, cis 45 plus 360k over 3. And then we have the cube root of 2, which we can't really simplify. 45 over 3 is 15. 360k over 3 is 120k. So we can start with 15 degrees, add 120 to it each time. So we get cube root of 2, cis 15. Cube root of 2, cis 135. Cube root of 2, cis 255. And again, going beyond that, we're just going to cycle between these 3 values. Now, as far as exact answers go, 15, 135. Well, we do have one for 135, but 15 and 255, we'd have to use angle sum and difference identities, and it's too much work to do those, so we'll keep them as they are. All right, finally, example 5D, the 5 fifth roots of z equals 1. So if you were to solve something like x to the 5th power equals 1 in college algebra, you get a total of 5 zeros, one of which is real. The others are, I believe, are all imaginary, but in any event, z in its polar form is 1 cis 0, because we have 1 plus 0i, 1 cis 0, which is 1 cis 0 plus 360k over 5, and that gives us cis 0 plus 72k. So here's our real solution, 1 cis 0. This should actually be 1 cis 0. And then cis 72, 1 cis 44, 1 cis 216, 1 cis 288. Actually, 1 cis 0 is 1. So, taking the 5th root of 1 is 1. So here's our real number, and then these other 4 are imaginary. So that about does it for this video and this section. You should be good to go for the rest of the problems. So I will see you next time.